a small detail, I do not know whether you will have time to implement it. Now, delta t, when I plot it for short times, you can have an array just the way I have written here, and of course, you have to average over different number of particles and different number of times, where you will write down x 2 minus x 1 at a certain position of the array, and so on so forth. What one can typically do is take an array with delta t equal to 1, 2, 3, 4, 5, 6 so on for small time displacements, because if you need an array, if you have to save the position of all the particles for around 1 million and you have 5,000 particles and you are saving them for 1 million time, the array to calculate the diffusion constant, the amount of space, the memory, the array that you have to take to save the position of all these particles is extremely large. It is 1 million times 5,000, right. Whereas, especially at long times, you do not need to save the difference in positions at each time, right. You can save it every 100 iterations and or every 1000 iterations, especially when you are looking at differences, the displacements and 10,000 at a displacement at number of iteration differences of 10,000. So, you do not need to save it at 10,000 iterations, 10,001 iterations, 10,002 iterations, especially since you are using a log scale. What you could well do is save the difference in positions at 10,000 iterations, 20,000 iterations, 30,000 iterations, 40,000 iterations, and then thus average the displacement over that. For small times, however, you shall need to save the displacements at each instant in time. That is what will give you this part, right. Whereas, for this part you can have a different array where you save the positions only after every 10,000 or say after every 1,000 iteration, and then you are done, right, to calculate the difference in the positions. Now, there is one more thing you should keep track of. Now, if you just keep the positions of the particles, remember that over long times particles are going to cross periodic boundary conditions, right. So, if you just save the positions and calculate x 2 minus x 1, you are likely to get wrong values of x 2 minus x 1, because the particle might have started out somewhere in space, then cross the periodic boundary condition, and after say 1 million iterations, it is somewhere close to its starting point. So, whereas x 2 minus x 1 should be relatively a large number, depends upon the diffusion constant as well. Actually, the due to the presence of periodic boundary conditions can give you a misleading answer. So, what you should save is not the position of the particles, but every time you update the position in your update position subroutine, there itself you should be keeping track about what is the displacement in time delta t, what is the displacement in time 2 delta t. So, this displacement where what I am talking about is really the V t plus half A t square and not calculated from x 2 minus x 1. So, you have to keep track of the displacement and not the positions. If you make this mistake, you are going to get ridiculous values of the diffusion constant, you are not going to get the diffusive regime. Please think about it. Okay. So, you have to incorporate the periodic boundary conditions in your calculation of your mean square displacement, and what you really need is the displacement and not difference in positions, because that could give a misleading answer. Okay. So, finally, I will end this lecture with a test for molecular dynamics simulations. You know, molecular dynamics simulations, even the update of positions and velocities, especially the calculation of forces, especially if you have complicated forces, much more complicated than the Lennard-Jones we discussed, errors can creep in the calculation of forces, and one needs a very robust test to ensure that your molecular dynamic simulations is working correctly even before you go to calculate statistical quantities. Okay. So, this is something which you do not typically find in the books, but this is a test by which you can weed out any tiny errors that might remain due to whatever the delta t not working, or some small errors at the cutoff, whatever be the errors. This is the test by which you can really catch any tiny error. Okay. So, let us start in discussing the test in greater detail. Now, what you have already told and what I have already shown in one of my previous recordings, that when you start from a random initial condition and start a molecular dynamics, then you have an initial position, you often need to switch on the thermostat, right. And in that case, as the particles move around and exchange kinetic energy and potential energy with each other, the kinetic energy could keep on increasing. As a consequence, plotting the energy per particle, the energy is going to look like this. I mean, it is that it is constant and it is conserved for a certain amount of time till you call the thermostat, and then the energy readjusts itself. It could drop, it could go up as well, but most cases you see a drop, and then energy again remains constant for some time, and then it drops, and then it remains constant for some time, and so on and so forth. The drop is fast towards the initial start of after the initial start of the simulation, but gradually it goes into a flat line, and then energy could either slightly increase or decrease as you call the thermostat, and correspondingly the kinetic energy typically grows up. But when you call the thermostat, it is readjusted energy per particle to 1.5 kBT, assuming kBT to be equal to 1. Of course, if it is kBT is higher, this will be 1.5 kBT. And then as the MD goes on, the kinetic energy increases and then drops again and so on and so forth, and this drop in the kinetic energy relatively decreases as you further run the MD system, and the system goes towards equilibrium, and once equilibrium is reached, what you see is basically kinetic energy fluctuates about an average even as you call the thermostat. There is very tiny nearly jumps in the kinetic energy which are not discernible in this scale, where you have plotted the kinetic energy, the total energy and the potential energy. So, all that you have been doing is rescaling the kinetic energy to reach the equilibrium for which total energy has been adjusting itself, but typically the potential energy does not show any jump. However, the kinetic energy increases because some of the potential energy is being converted to kinetic energy. So, typically as at least for the Lennard-Jones case, you know, see some a decrease in the average potential energy of the system as the simulation goes on, as the particles readjust themselves and sit close to the potential minima, and it could form clusters of particles as well, depends upon the density, and then it starts to fluctuate about the equilibrium. So, that is how you identify equilibrium, right, that the kinetic energy, the potential energy and the total energy is fluctuating about an average value, and after this point you can calculate that average value and calculate the statistical equilibrium energy, the potential energy, the kinetic energy at that temperature after it has reached equilibrium. Yes. Now, this is the standard molecular dynamics simulations. Now, what one should do for the test, I am I am basically discussing a test for molecular dynamics. The first thing you do is you start with the system in the presence of a thermostat and allow the system to equilibrate. Suppose the system takes around 50,000 iterations after the system reaches equilibrium. Then you stop the MD. Okay, you just stop the MD because your aim is to test whether your code is working perfectly. Of course, if you wanted to measure some things, you could continue with the MD. And after the stopping the MD, you could store the final position and velocities of the now equilibrated configurations. Now, you have the positions and velocities of all the particles written in two different files or maybe same file. Now, what you have to do is, starting from this positions and velocities. So, you are going to restart the MD, but the initial position and the velocities of all the particles have to be the stored positions after equilibrium. Okay. And now, you switch off the thermostat, you comment out the thermostat line and you restart the MD with the initial position and velocities of the equilibrated configuration and run the MD without the thermostat, say for p iterations, p being 1000 iterations. What will you see is, with the thermostat switched off, that the total energy is absolutely constant, the potential energy is fluctuating, and correspondingly whenever potential energy shows a peak, kinetic energy will show a corresponding dip, and whenever potential energy shows a peak, the kinetic energy could show a dip, and so on and so forth, right. That is how you have the total energy constant, especially if you look at it in the same scale where you have plotted kinetic energy, total energy per particle and the potential energy per particle on the same graph. But if you decided to zoom in at the total energy and zoom in really in great detail, so that basically, as I discussed before, that the energy is going to remain constant, but it is going to fluctuate at the scale of delta t square. So, if your delta t is 0.005, suppose you zoom into 10 to the power minus 5 or something like that, because right 10 to the minus 6 or 10 to the minus 5, then what are you going to see? You are going to see fluctuations in the total energy, this green line, suppose, right, with delta t equal to 0.005. Now, if you restart the simulation from the same initial condition as before, which is that equilibrated positions and velocities. So, you are starting exactly from the same initial condition as before, but with delta t, the integration time, to be half that of the previous value, which is 0.0025 say, and you run, since you have since you have a lower value of the delta time, the integration time constant, to run it for the same time, you have to run it for 2000 iterations, if your previous number of iterations was 1000. So, that the total time elapsed in that test run, you are testing the molecular dynamic simulations with 1000 iterations or whatever be the number p1 number of iterations. So, that p1 delta t1 remains p2 delta t2, where delta t2 is the smaller integration time constant. And now, you plot the total energy again and zoom in. Of course, on this scale it is going to remain, it is going to appear to remain exactly on top of each other, because the total energy is constant, right. And but if you zoom in, then you are going to see that the trajectory of the energy in this graph, where you are plotting total energy per particle versus time, the length of the simulation, the time elapsed in the simulation short run is the same, then it is going to exactly follow these peaks and dips in the energy. Look at this blue line, right. You are going to reproduce it in your simulations, and so you see that wherever there are peaks also here, but the height of the peaks or the depth of the valleys wherever there is a dip, that is around 1/4 that of the previous value. Is basically the fluctuations in energy. What is fluctuations in energy? E square average minus E average square, which you can calculate for both these two cases, right. The fluctuations in energy delta E. So, basically you are saying that the delta E with larger delta T 1 is 4 times that of the delta E, the fluctuations in energy with the smaller integration constant, and this is 4 times because you have halved the integration. Of course, if you had made it 1/3, then this relation would be 9 times. So, the fluctuations in one would be 9 times than the other, than the one with the smaller integration time constant, right. Now, the average of the two energies will be exactly the same. It will absolutely follow the path. On the other hand, if there is a bug somehow, so then you will see that this does not follow the exact path. The average will not be exactly on top of each other. It might be shifted in some way. These would be extremely tiny mistakes which can creep in. And so, that is what a test that is how, I mean, if this works perfectly, there you can be assured that you do not have a bug in your code. Of course, if you keep on increasing delta t say to 0.01 say, then you will see that the integration itself is not working properly. The energy shows a shift, the particles move around and basically sit on top of each other, because the Newton's equations of motion are not being integrated properly. As a consequence, the MD is going to show an error. Two particles can come too close to each other, form or face a very large value of the force, because it has moved unphysically close to each other, which will lead them to be kicked and sent away from the box, and you typically get a code dump. Your code stops running. And so, depending upon the potential, you have to choose a suitable value, small value of the integration constant. The sharper your potential, the smaller integration constant you have to choose, right. The last thing I think I need to tell you, and which I might have forgotten to tell you, is often for equilibrating your system, you switch on the thermostat in a molecular dynamics, but after the system has equilibrated, whether you keep the when you are calculating your statistical quantities of interest. Now, whether you keep the thermostat on or off depends upon the physics of the problem, depends upon what you want to study. If you want to study the system in a microcanonical ensemble where there are no energy fluctuations allowed, then you keep the thermostat off, and then the energy will be perfectly conserved. On the other hand, if you are fine looking at the system in a canonical system, canonical ensemble, then you can study your system with a thermostat switched on, which will maintain the right temperature. Anyway, since the system is already equilibrated, even if you switch off the thermostat, there will be only extremely small deviations from the right value of temperature, which you can use which you can calculate using the equipartition theorem. So, it is basically going to fluctuate about an average, because whatever extraneous kinetic energy and potential energy exchange was there, that you have already taken it out using the thermostat, right. So, this basically brings out to the end of this course of molecular dynamics simulations and end of this course. Of course, there are many kinds of thermostats, there are a lot of other things which can be calculated using molecular dynamics, but we hope that with this amount you have at least got some exposure to molecular dynamics, and in more general various computational techniques, various flavors of them, various kinds of problems which can be solved. So, that in future whenever you need to solve a computational problem, you will be capable to read up the algorithm from a book or learn it from your supervisor, and be able to implement it on the code. Very importantly, you always need to use your physics intuition to devise tests. Why should you believe that your code which you have written is working correctly? There are more often than not bugs, there are always bugs, and one has to always devise tests such as conservation of energy, conservation of momentum, whether density is uniform or not, whether you are getting correct diffusive behavior or not, or even better tests like the one we discussed to ensure that you are getting the right code. Moreover, even while you are calculating statistical physics, statistical quantities, whether you have got a good average or not, all these have to be tested using ideas of physics. And whatever problem you do in your future, wherever you use computational physics, you have to use your background intuition, the background science, physics or whatever, to somehow test whether things are right or not, and then only then go ahead and calculate non-trivial quantities which will be of interest for the future. Right. With that word of advice, I shall end this course, and thank you for your attention.